So you can see from the title, I'll be giving you a broad overview of electric dipole moments of particles as probes of new physics, and I'll culminate the talk with some words about the glorious future of EDM searches. I was jealous of, I think it was Ben Safdie's title, Why Axions Could Be the Next Big Discovery in Physics. I should have called this Why EDMs Could Be the Next Big Discovery in Physics. So just start by pointing out that it's long been understood in the particle physics community that T violation, or equivalently CP violation, since CPT is known to be an extremely good symmetry, is really a powerful window into new physics. And let me try to make this argument. So the first is we know that time reversal, or CP symmetry, is broken in nature. This was observed already many decades ago, been studied in great detail, and T violation is always associated with some dimensionless number, a phase angle that appears in a complex number, e to the I delta. So the enormous amount of effort that's been put into studying CP or T violation in the particle physics community is all consistent with the single explanation that it comes from a single phase angle in the quark mixing matrix, the CKM matrix. And I'll point out this phase angle is almost 1 radian, so it's not a small effect at all. It's just that it's sort of buried in a detail, a corner of the standard model. So the T violation in the standard model, in the sense that it comes in only through this back door because there are 3 quark generations, seems sort of peculiar and minimal in the sense of quantum field theories broadly construed. It turns out that if you take the standard model and add new physics, new quantum fields to it, it's actually typical that adding those new degrees of freedom will allow new time reversal violating phases. And the fact that the matter greatly dominates over antimatter in the universe is understood to require additional T violation from beyond the standard model. So T is broken. It's broken in an almost maximal way, but with a peculiar mechanism. We know that new T violation has to happen, and it's easy to construct theories where it happens, and in fact, difficult to construct theories where it doesn't. So, what does this have to do with electric dipole moments? If you imagine a particle with an electric dipole moment along its spin axis, here showing an electron with a little bulge on one end and a dent on the other to indicate the dipole moment. If you take this system and you do a time reversal transformation, the spin changes direction, but the dipole moment, which is a static charge distribution, doesn't. So if all electrons or protons or mercury nuclei, any quantum particle, if they look like this, then the time reverse version doesn't exist and time reversal is broken. So looking for EDMs is a way to look for time reversal. To connect those to particle physics, it's easy to think about the analogy to magnetic moments. So we know, for example, in the standard model, the electron's G factor, magnetic G factor, is 2 in Dirac theory, exactly 2. But in quantum electrodynamics, G differs a little from 2. And the lowest order process associated with that is the electron emitting and then emitting a virtual photon and then reabsorbing it. This is, of course, the famous QED correction to G minus 2. But you can extend this idea to more complicated processes. This is another contribution to G minus 2 in the standard model. And if you're not familiar with these, the way to read these Feynman diagrams for our purposes is to notice that the heavier the particles in this diagram, the smaller the effect. the effect scales like 1 over the mass squared of the heaviest particle in the diagram, and the number of loops corresponds to the order of perturbation theory. So the electron and all particles, quarks, and so on, have electric dipole moments in the standard model because T violation is broken. But it turns out it's deeply suppressed in the standard model. So here's a typical lowest order contributor to the electron's electric dipole moment in the standard model. You can see that it involves 4 loops, and it turns out there's a symmetry of the standard model that results in severe cancellations when you add up all possible diagrams of this type. So for example, the electron EDM predicted value in the standard model is effectively about 9 orders of magnitude below the current experimental limits. So there's a huge range where you can discover something new before you run into a background from the standard model. In theories that extend the standard model, for example, simple supersymmetric theories, the electron can acquire an EDM from a single loop diagram, and there's no obvious mechanism to add up diagrams and have them cancel. So this means that in these theories, the electron EDM can be much larger than in the standard model. And this is not just relevant to supersymmetry, but also to many other models that extend the standard model. So it's easy to write a sort of dimensional hand-waving estimate for how large you would expect an electric dipole moment to be if it's associated with a virtual emission and reabsorption of some heavy new particle and some T-violating phase. And with sort of natural assumptions, CP violating phase of order a radian, like in the standard model, couplings like electromagnetic couplings, you can write down this simple estimate for the electron EDM. And if you plug in numbers, you find that the current limit on the electron EDM in this hand-waving estimate for a single loop diagram would already be probing masses of new particles in the range of 50 TeV. And as a reminder, the Large Hadron Collider is only able to probe up to order a couple of TeV, 1, 2, 3 TeV, depending on the particle. Electrons, again, can get EDMs from multiple sources. Different sources actually give different contributions or are sensitive to different masses of new particles. We're actually over a broad range depending on the model you're testing, but I'll just stick with this simple single loop diagram as a benchmark for mass scales that we're probing. So it's not only electrons, but also quarks can acquire electric dipole moments from new physics in the same sort of new physics that gives an electron dipole moment will also give a quark dipole moment. And there's an additional mechanism, which is actually a piece of the standard model. It's CP violating strong interaction over on the right there. And it's known from EDM experiments that this theta parameter that is a dimensionless number that characterizes the strength of this CP violation in the strong interaction is less than 10 to the minus 10. So looking for, and quark EDMs will then, quark EDMs and also the strong interaction analog of EDMs, so-called chromo EDM, where the new physics couples to gluons. Both of these lead to EDMs in nuclei, which are, of course, filled with quarks. It's also worth pointing out that axion dark matter is equivalent to an oscillating value of that parameter theta. So if axions are dark matter, it'll cause quark chromo EDMs and nuclear EDMs to oscillate at the same frequency of the axion field. So here's a sort of broad overview from Matt Rees at Harvard, who's a real theorist, that kind of shows as a plot of the mass range that's been probed in experiments versus how generic the processes are. So the most generic is particles that couple only via electroweak forces. Next, particles that also interact via the strong force. And then CP violation at 2 loops is pretty general, 1 loop is less general, and then flavor violation probes extremely high scales, but is the least generic sort of process. So, okay, I don't know what happened to my animations there. So how do we look for EDMs? Well, we take the spins of the particles we're interested in, we spin polarize them using typically laser optical pumping. Then we apply a magnetic field and an electric field parallel to each other. They cause the magnetic field causes the magnetic moment and the spin to precess around the magnetic field. If the particle has an EDM, the precession will be a little bit bigger or smaller, depending on the size of the EDM. And then we can flip the electric field back and forth and look for a shift in this energy splitting between spin up and spin down. So the figure merit for statistical sensitivity for experiments like this is the energy shift over the energy resolution. It depends on the electric field experienced by the particles, the spin coherence time, and then the square root of the counting rate and the integration time. Integration time is a constant of nature set by how long the graduate students are willing to sit in the basement and flip the electric field. What's surprising is that already many decades ago, Schiff pointed out that in a neutral atom or a neutral molecule, even if you apply an electric field to that system, the individual particles in the system feel net zero electric field, as if they didn't, they would fly away. But Schiff already understood how to avoid this theorem because this conclusion only holds for point-like non-relativistic particles. So what matters for the electron is the electron moves very relativistically when it gets near the nucleus in a heavy atom or molecule. And this, in fact, leads to a non-zero energy shift, which we can characterize as an effective E field, even though it's not a net E field. For nuclei, what matters is that they have a finite size. And essentially, if a finite-sized nucleus has an electric dipole moment, it corresponds to a surface charge distribution that produces a dipole field outside, but also a constant electric field inside. And then electrons in an atom or molecule can go inside the nucleus and probe this internal electric field. So this finite size effect is called a nuclear Schiff moment. And for all intents and purposes, it acts like an EDM. So, big breakthrough in the last decade or so, maybe 15 years, is increasing use of molecules to look for EDMs. And the reason is because molecules are easily polarized by external fields, they enhance the effective fields felt by an electron or by a nucleus inside the molecule. And to give you a sense of how big an enhancement this is, for electron EDM experiments, the effective electric field ranges from roughly 15 gigavolts per centimeter in experiments that you'll hear about, up to about 80 gigavolts per centimeter. The effect is smaller on nuclei, but still much bigger fields than you can apply directly in the lab. So, state of the art for the electron EDM is a molecular beam experiment called ACME that I work on, and a beautiful experiment from the group at Gila. And what's striking is that the coherence times here differ by more than 3 orders of magnitude. The count rates here differ by roughly 6 orders of magnitude. and yet they give results that are quite comparable to each other. State of the art for nuclear EDMs is an experiment using room temperature vapor cells of mercury atoms at University of Washington, and we're working on a molecular beam experiment where we expect to get sensitivity similar to what was done in the mercury experiment. A big trend in the field is to use nuclei that are pear-shaped. These deformed nuclei are easy to polarize, and the effect of a quark EDM in there, or quark chromo EDM, is enhanced by factors of 100 to 1,000 compared to the case of mercury, for example. Almost all of the nuclei, and definitely the ones where this effect is biggest, are radioactive. So that means that many people are trying to work with radioactive molecules. Point out that there's also growing interest in looking at EDMs in solid-state systems. They can give you much higher statistics than gas phase experiments, and methods for efficient optical state preparation and readout, relatively long coherence times, and very clever ideas for control over systematic errors are making this look quite attractive, and we'll hear about this from Amar Bhutha later, who's really been the pioneer in developing these techniques. Of course, in modern atomic physics, almost all the experiments use laser-cooled and trapped atoms. They're very powerful techniques. So it's kind of striking that all the current gas phase EDM experiments have temperatures of a few Kelvin or even higher. So many of us are trying to use the methods of modern atomic physics, using, for example, direct laser cooling of molecules. And we'll hear some of that effort from Mike Tarbit's group. Another way to make ultracold molecules is to take ultracold atoms and stitch them together to form molecules. This is an extremely successful technique for alkali atoms. And this technique has enabled, for example, coherence times of nuclear spins in excess of 5 seconds already. Trying to leverage that, we formed a collaboration we call Red Rum, and you'll hear from Alan Jameson about that later this morning. But the basic idea of Red Rum is to try to form a molecule with a deformed nucleus francium and another atom to make it a good polar molecule, assemble the molecules out of ultracold atoms, and hold them in an optical lattice. So this is my final slide, just to point out, with these new techniques of ultracold molecules, we think it's going to be possible to go much further in the search for quark chromo EDMs. This plot shows on the left panel the mass scale of new particles that's probed. On the right scale, the size of the quark chromo EDM. These are ongoing experiments. We think that Red Rum can do a couple thousand times better than this in its first generation, and that future generations can plausibly go up by another few orders of magnitude. So that would correspond to probing energy scales well above 1,000 TeV. So you'll have to start thinking about the PeV scale in the near future. So with that, I'll end, and thank you.